Thank you very much for the invitation. I'm happy to be here and meet some colleagues and friends. And yeah, so I was, when deciding with Enrique about what to explain today, we decided to go for this topic. So here there are things that you may sort of know, which is Bell theorem, but I will also discuss it here. And some of the main purpose of my talk is to introduce you on this paradigm or scenario for quantum information application that is called device independent, that it's one of the main topics in my group. So I'm an ICREA professor working at ICFO, where I have a group working on many aspects of, say, quantum physics, quantum information technologies, but also quantum thermodynamics, the foundation of quantum physics. Now, all my talk is going to move from, say, technologies to foundations. So I'm going to jump from one to the other, and I think this is one of the aspects that I like of this device-independent scenario. Okay, that you can, as you will see, you can address some fundamental questions in quantum physics, but you can also think about possible applications of quantum phenomena for information processing. So let's start. If I can. I don't know what happens now. He doesn't like me. Maybe I should go like this. No. Ah, here, maybe. I don't know. Yes. Yes, okay. Now. So, well, I will start with, I mean, I believe that your backgrounds might be diverse, and I see young people, so I assume that you don't know a lot about quantum information theories. I will start by stating sort of quite simple things, I would say. So my field is quantum information science. I mean, this covers theory and experiments. I'm a theorist, and basically what the field tries to understand is what happens when you make this transition for information. Okay, so you want to understand what happens when you encode information on quantum particles. So physicists, they already made this transition starting at the end of 19th century and 20th century. They already made this transition. Okay, so they found out at the end of the 19th century that there were some experiments at a microscopic scale that could not be described by Newtonian physics. So they had to invent a new theory for that, and that was quantum mechanics. Okay, so this has already been achieved by physicists. So now we are more or less facing the same problem, but for information. Okay, so what we're trying to do is the transition from what you can do with information at these scales, and this is what we do today with our computers and mobile devices, internet, whatever. And then we want to do this transition and see what happens when we encode information on quantum particles. So if I give a general talk, I like to spend some time here, because I think what we now know is that you have new things that become possible thanks to quantum effects when making this transition. Okay, so you have more powerful computers, and you have different forms of secure cryptography. And I want to spend some time here because I think this is an important lesson of quantum information science. So if you had asked me when I was a student whether I thought that by using quantum physics you can do different things with information, I would have said no. Okay, because at that time I thought that one of the merits of information theory was that information is a bit no matter which physics you use. Okay, so I can communicate with you, and I can send you bits. This may encode a 0 and this may encode a 1. I can send you this and we can communicate with this. This is as good as the way we communicate. Of course, practically it's not good. Okay, this is why we do it with light. But at my time, I understand that information is decoupled from physics. Actually, I didn't take any course on information theory while I was a physicist. So what one of the first lessons we understand when we do quantum information theory or science is that if you care about information, physics matters. So there are some things you can do with classical physics, and there are some other things you can do with quantum physics. Okay? And this is because information is encoded on physical devices, so the laws of physics governing the devices where you encode information matter. I think this is a change of paradigm, at least in my understanding of information. Okay, so the field is evolving, and this also explains why I have so many logos, because there is funding, and you can you can do research, okay? And this is because it seems that you will have, I mean, information is a key concept in our society, and it seems you will have better computing devices, you will have new possibilities thanks to quantum effects. And I mean, there were first theoretical ideas, then proof of principle demonstrations in labs, and now we even have commercial products. Okay, so now you can go, and there are some companies that are giving you quantum computers. maybe not at the commercial level, but in some labs, people are doing what is called quantum simulators. So you try to simulate a system with another quantum system in a controlled manner in the labs. You can buy also some devices that allow you to send private information to a friend. This is quantum cryptography. So you encrypt messages using quantum phenomena. Or there are also quantum random number generators. So you have generators of random numbers based on quantum physics. Okay, so this is, you have these products in the market. The market is not super large at the moment. Hopes are that it will grow. And one of the questions I want you to understand is that, okay, usually you pay a lot of money for these devices because they are not cheap. And now you may wonder, okay, is this a proper quantum computer? Is this cryptographically secure? Is this quantum random, or does this achieve what it has to achieve? Okay, so this is a question that is very relevant and timely at the moment, and it covers basically any application. It's the question of quantum certification. Okay, so my talk, this is one of the key concepts I want to explain you. Now is a time to understand how we can certify properties of quantum system. And it's relevant also, and I will just want you to think about this, is because you should understand that, for instance, you will pay a lot of money for these devices, okay, say for a quantum computer, and all what happens is that you go to a provider and you say, like, I saw a talk by Antonio Acin and I want to buy a quantum computer. And the provider will tell you, sure, here's the quantum computer, and it costs a lot, okay? And then you will look at it and say, but is this quantum? And the provider will tell you, yes, it is. Okay, we don't want to do that, okay? So we want to have tools to certify that something is achieving what it is supposed to be. So we want to certify quantumness. And we want to do it precisely in this way, okay? So you will get a device from the provider, and you are a user, and, well, you know quantum physics, but in general, you don't know quantum physics. And you are never going to open the device and see that in the device you have photons or spins or ions or whatever, okay? You don't want to do that. You want to do it from the outside. And I always use this joke. I mean, if you have seen any of my talks, probably you have seen this joke, but I believe many of you are young, so you have not seen, because it's excellent for what I want to say, okay? So this is a Dilber, and you can understand this is the user, Dilber, who goes to the provider, and the user wants to buy a random number generator, even quantum, and this is the device, the say, even quantum random number generator, okay? The provider tells you, yeah, yes, it is quantum, okay? And then the random number generator gives you this sequence, and, well, you may wonder whether this is random, okay? Because you know that the probability of a proper random number generator to give this sequence is the same as any other sequence. Okay, so he says, well, you can never be sure about randomness. But you see, they are macroscopic objects. They live in the classical world, and they are thinking classically. So one of the goals of my talk is to demonstrate you that you can be sure about randomness in quantum physics, okay? Which sounds paradoxical, but it's not, okay? But this is what we want to do, okay? As an example, is we want to see how you, as a user, get a device, quantum random number generator, and you can be confident that this is a proper quantum random number generator. Okay, and in general, we want to certify devices from the outputs, the statistics they produce. Okay, so this is more or less the moral for my talk. This problem is relevant in many scenarios, but it's particularly relevant in cryptographic scenarios. So in cryptography, I don't know, I want to send a very private message with Enrique. I don't have any super private with him, but let's suppose I had. Okay, so I had to secure a message with him, and there is an enemy who wants to read this information. So it's very critical to understand what are the possibilities by the enemy. So for that, there is something that is called quantum key distribution. It's a protocol based on quantum physics that allows you to encrypt information. And these protocols are secure, and they give you something that is called physical security. So why the protocol is secure? Because, okay, I'm going to send the information to Enrique using photons, which are quantum particles, let's say. Any enemy who tries to play with this information will be bounded by the laws of quantum physics. I will assume that the enemy can do whatever, the enemy is usually called Eve, and we're going to use she, because this is the standard terminology. So the enemy can do whatever she wants, but she cannot break the laws of quantum physics. This is what I assume, okay? This for us is not an assumption, but for some people it's an assumption, okay? So I assume that the enemy's actions can be arbitrary, but compatible with quantum physics. And then using this property, you can have a protocol in which you can prove that the protocol is secure and it allows you secure communication. I'm not going to explain how it works, okay? Just to tell you that using the laws of quantum physics, you can design a method for secure information transmission. So this is nice because you take the postulates of quantum physics and you derive a security proof for the protocol that guarantees that I can safely send the message to Enrique. Okay, and in fact, there are companies that sell you these devices, okay? So I know some of the companies. I may even get you a discount if you are interested, but it's not cheap, okay? So this is an expensive device. Very nice, there is a security proof, so there is some sort of mathematical stamp that tells you this is secure. There are companies, you can buy them. Now, around 15 years ago, there were several teams of researchers. In particular, there was Vadim Makarov and co-workers who was especially active in that. They went to these companies that were selling quantum cryptography, secure quantum cryptography, and they took them and they hacked them. Okay, so they proved that they could hack the quantum cryptography devices. Well, they published a nice paper, also Nature, in Nature Photonics. Nature was commenting about that. And it was a surprise for the field, okay, because there is a mathematical security proof that tells you that this is secure, okay? So how can it be that Makarov hacked something for which there is a security proof? Now, there are several possibilities, okay, because I was telling you that there is a security proof based on quantum physics, okay? So, I mean, the hackers usually are conceived as bad people, but it depends, okay? So I think a cryptographic method is not mature if it has not been exposed to hackers. Okay, I think this is needed. This is good for a field to have hackers. Sometimes hackers collaborate with providers, and in this case, Makarov was providing. Okay, he didn't hack and didn't say to anybody that had a successful attack. He communicated how the hacking attack worked. Okay, and that was good for the provider to improve the devices. But now, how could it be that he hacked? Okay, so I was telling you there is a mathematical security proof based on quantum physics. So let's think about what happened. So maybe Makarov found a mistake in the mathematical security proof, okay? Does he look like a mathematician? Not really, okay? You see, he has a lot of devices around him. He's an experimentalist. He's not a mathematician. So this is not what he did. Now there is another possibility. Maybe he proved that quantum theory does not offer a correct description, okay? He proved quantum physics to be wrong. Well, no, okay? So he would have won immediately the Nobel Prize. This is not what he did. So we understood that he was doing something different. So what was he doing? So what the hackers were doing, or what the hacking attacks do, they want to break the implementation, not the principle. So, and by this I mean the following. So if you look at any quantum key distribution protocol, it tells you, I mean, maybe you know it, maybe you don't know it, it's not so relevant, but basically the protocol tells you, me as a sender, I have to prepare these quantum states, and these quantum states live in a Hilbert space, usually of dimension 2. These are called qubits, okay? So spin 1/2 particles or photons with polarization. And then I send these quantum particles in these quantum states to Enrique, and Enrique makes some operations, usually measurements, and these measurements are defined by bases in a Hilbert space. If you remember quantum physics, textbook quantum physics, okay, a measurement is a basis in a Hilbert space. And then based on this process, we construct the secret key. Okay, so this is what the theory says, and it tells you prepare these states in this Hilbert space, make these measurements in this Hilbert space, and you have the secret key mathematically proven. Okay, there's a security proof here. But now what does the provider do? Well, I mean, we don't know how prepare a system that exactly lives in a Hilbert space of dimension 2. Okay, so if you think about it, dimension is not something that you bound. Okay, it's something that you associate to system. It tells you how many degrees of freedom you are interacting with. Okay, but I mean, any particle has many degrees of freedom. I would even say infinite. Okay, so if I put information on a photon in polarization, yes, it is true that polarization spans a space of dimension 2, but a photon has a frequency, it has orbital angular momentum, it has many degrees of freedom. Okay, so I think it's a very strong assumption, and I think it's even impossible to see that you are only using 2 degrees of freedom. So this condition is very hard to meet in practice. Okay. So basically usually what the providers do to prepare these states are using an attenuated laser source. I don't think anyone is going to say that a laser source lives in a Hilbert space of dimension 2. Okay, this is not true. And then the measurements, usually they are defined in quantum physics by matrices, and usually it's a spin 1/2 observable. These are 2 × 2 matrix. But actually the measurement is a single photon detector. Okay, again, I don't think a single photon detector can be described by a 2 × 2 matrix. Okay, no way. By this, what I'm saying is that you have here some theoretical requirements that are needed for the protocol, but they are never perfectly met by the implementation. There is always a gap between what the theory demands and what the implementation does. So you have a security proof here, but the hackers, they don't care, okay, because they want to break the implementation. So and this is why they are able to hack it, despite the fact that there is this theoretical security proof, okay, because there is always a mismatch between these two realizations. So the moral is that it is very nice that we have that information depends on security. It is also very nice, in my opinion, that you can make protocols secure based on the laws of quantum physics. But if the security of your protocol depends on many physical details of your implementation, like you have to be sure of preparing these states in this Hilbert space with these measurements in this Hilbert space, this may be a problem, okay? Because if you don't meet these requirements in your implementation, then this may open security loopholes. Okay, so it's very nice to have physical security, but it has to be the amount of physics you need, the amount of modeling you need has to be minimum. Okay, so I don't want to make these assumptions about my devices and conclude that something is secure. So this is what I want to do, okay? So, and this connects to what I was telling you before, okay? So what I want to do protocols in which I can see my devices as boxes I get from a provider. So if I can prove something only using this, in this black box scenario, then there won't be any mismatch by theory and experiment, okay? So what I'm demanding is that Alice and Bob, that are usually the parties that want to exchange private information, before it was Enrique and me, now they will become Alice and Bob. This is, again, standard terminology. So Alice and Bob, they want to exchange messages, and they buy devices from a provider. And again, I want to see these devices as boxes they get from the provider. And of course, they have to interact with these devices. So how do we interact with devices? As we interact with classical information. So they will give some value, some classical information to the device, and the device will give some output. So Alice will give some variable x that can take n values and to the device, and something will happen here. I don't know. I'm never going to open the device. I'm never going to see what is inside the device. But the device does a process, possibly a quantum process here, and produces the output given the input. And what we read usually is classical information. We don't read quantum states, okay? We always read classical information. So this is going to be a classical variable input producing an output, and Bob will have the same. So if you want to think about what I'm having in mind here, this is a possible realization. You have this device, and this device has n buttons. Okay, you see them with your eyes. And you can press button 1, button 2, button 3, button 4, button 4, button M. This is the way you provide information to the device. You can give it as a list of bits, okay? But if you want to think in another possible way, it's just you press one of the buttons, okay? This is the way you interact with your device. Or you have a knob that you can put in different positions. This is what I'm labeling here. And then the device at the bottom, it has some lights, and whenever you press one of the buttons, one of the lights is on. And this is your result. It can be this, it can be a click in a detector, it can be a musical tone, it can be a color. I mean, it doesn't matter, okay? These are just labels that I will put to the actions. So Alice and Bob go to the provider. They don't want to trust what the provider tells them. The provider may say that something is quantum, but they don't want to open the box. Now they will spend some time pressing buttons and observing lights, okay? Or putting inputs and getting outputs. They do it, so they are testing the devices, and they count how many times they get result A and B when they press button X and Y. And you count frequencies and they define probabilities. This is standard statistics. I'm not inventing anything. Now, if you are able to conclude that this statistic allows you to perform a protocol, like distributing information in a secure way, then there is no mismatch between theory and implementation. Okay? Because all what the theory demands is that you observe some given statistics, and all what you have to see in the experiment is to observe that statistics. I'm not saying that this is a qubit, qubit, infinite dimensional system, quantum, classical. I'm not saying anything. All what I want is that these devices produce these statistics. If I see the statistics, I buy the devices. If I don't see the statistics, I send the devices back to the provider. Okay, so this is why this black box approach to information processing is so useful in this context. Okay, and again, I don't need to put any trust in the provider. I buy the devices, I test them. If they are good, I keep them. If not, I send them back. And being good and bad, it's a test that for which I don't need to open the devices. It's simply coming from the statistics that the devices generate. Okay, so this is the device-independent paradigm, and it's called device-independent because you want to reach conclusions independently of the inner working of the devices. So I don't know how the devices produce the output given the input, but I know that the statistics is good enough for my purposes. So I was told that usually questions come at the end, but they may come while I speak, so if you have any questions, feel free to interrupt me. Okay, so this is just an introduction. So this is the device-independent approach. Okay, sometimes I call this device-independent approach like a quantum information theory for black boxes, or sometimes I also call it, it's a quantum information theory without Hilbert spaces. I never impose any Hilbert space. I don't say this is dimension 2, 3. I don't associate any Hilbert space to my device. Okay, this is what I'm going to do all the time. Okay, so this is the motivation for what I want to do. It comes from this certified working, trying to find protocols based on minimal assumptions on the devices. And more in general, okay, this is what I was telling you, it's a quantum information theory for black boxes in which you put inputs and outputs and you observe statistics. Okay, you can now have many more than 2 devices. Okay, so this is the first part. I was telling you that I will jump from foundations to more applied things and then back, okay? So all my introduction was more on the applied side, okay? You want to buy devices and make things with devices. So now we have to understand why I can do this sort of quantum information theory with black boxes. And now I will start talking about more formal foundational aspects. So in my explanation so far, I was telling you that Alice and Bob want to run cryptography. They go to the provider, okay, and the provider gives them 2 boxes, and then Alice and Bob go to or Enrique and I, we go to the provider in Madrid, okay, maybe, let's say, a common point, and then I go to Barcelona and he goes to Bilbao, okay? So Madrid, provider, you are Alice, Bilbao, and I'm in Barcelona, Bob for Barcelona, okay? And we are testing these devices. Okay. So now I'm going to do something that is very simple. I'm going to call the provider a source. Well, this is a Bell test. Okay, so a Bell test, I don't know if you know about the Bell test, I'm going to explain it, okay? But for those who know the Bell test, a Bell test is an experiment in which there is a source that prepares a state of 2 particles, and you make measurements on the 2 particles, and you get measurement results. It's nothing like this, at least, huh? It's the same. You see, it's not difficult to go from the previous explanation to the Bell test. Okay, I only have to change provider and call it a source that prepares 2 systems. Alice and Bob have these 2 systems, and they interact with the 2 systems. And the interaction that we usually have in Bell test is we make measurements, but we choose what to measure. Okay, so we have measurements, and measurement is putting a mirror in a given position. So it's also an action, and you get a measurement result. So all the narrative I was telling you is strongly connected to the narrative that you have in Bell test, in which you prepare devices and you give classical information to the devices, and the devices give you classical information, and you care about the statistics produced in this experiment. Actually, a Bell test, you don't invoke any physical theory to explain. So usually we see Bell test or Bell theorem in quantum physics, but Bell test has nothing quantum. It's just an experiment in which you make measurements, or you decide to make some actions on devices, and these devices give you output. Okay, and one of the main lessons of Bell's theorem is that the statistics you can see in an experiment, in a Bell test, depends a lot on the physical theory described in these experiments. Okay, so the way 2 devices or more devices can be correlated depends on whether the devices are classical or quantum. Okay, so the statistics I see among different devices depends on whether these devices are classical or quantum. So in all you see, it appears already in my explanation before about the devices, or now about the Bell test, which is basically the same language but changing a bit the words. It appears this object here, okay, which are the probability distributions of observing the outputs given the inputs. So this object, it's usually called the correlations. It tells you, if I see something here, what are the probabilities of seeing something there, okay? How devices are correlated. So this is the object I'm going to deal with. All my theory is going to base on this object, on correlations. So now we are going to become a bit formal on that, okay? So what is the object that we are going to use in this device-independent scenario? This probability. So what do I mean by this? Well, so far this is mathematics. So this is it will give the probabilities of all the possible combinations of inputs and outputs, okay? So for instance, there is a situation in which Alice presses button 1 and Bob presses button 1, and they see what are the probability of the outputs. So they may see result 1 and 1 here with a given probability, result 2 and 1 here with a given probability, and so on, up to result R and R. Okay, so this is a vector of R square numbers. They are probabilities, they are all positive, and they sum up to 1. If you sum over the result, it has to be 1, okay? We all agree with this. This is mathematics, okay? If not, this has to be clear, okay? But of course, here, there is also a situation in which Alice presses 1 and Bob presses 2. And then, again, they observe the outputs, okay? This would be positive numbers that sum up to 1, okay? And the same up to the last combination of M, M. So we'll have this, okay? So what I call correlations is nothing by all these probability distributions, okay, that you can put as a single vector, okay, of numbers, all positive, and having these normalization conditions. This is mathematics, okay? Okay, let's give an example so we can touch what I'm talking about, okay? So let me give the simplest example in which Alice and Bob use give a bit and produce a bit. I'm changing the notation a bit, but okay, you should not get confused. Sometimes I use 1 to M and 1 to R. Now I'm going to use 0, 1 and plus minus. Does it matter? Of course it doesn't, okay? These are just labels, okay? I can call the outputs Enrique and Antonio. Doesn't matter, okay? It's just probabilities. So now I use this convention, okay? 0 and 1 and plus and minus. So let's assume that when Alice uses 0 and Bob uses 0 as an input, they see that whenever Alice sees a plus, Bob sees a plus. This is like measuring singlet, okay? You know that the results, for those who know quantum physics, you know that when you get a result plus, a maximum tangent set of 2 qubits, the other person also gets plus. So the results are correlated. This happens with probability half, okay? This is, you see, I use 0 here, and whenever I see plus, I see a plus here, and this happens with probability half. Okay, this is telling me this number is half. Okay, you do it, okay? You make the experiment and you check this probability. Let's assume that, however, Alice may also see minus, but when she sees minus, Bob sees minus, and with probability half, okay? Okay, can you guess the value of these two numbers? Yes, okay? Clear. Okay, this is a potential experiment. It could happen that you have two devices in which you put an input, you make two measurements, and you get two outputs, and they behave like this. Actually, we have it, okay? So if you take a maximum tangent state of 2 qubits and you measure in the Z basis, for those who know quantum physics, you will get this distribution. Let's assume that the same happens when they use 0 and 1. Why not? 1 and 0. Why not? I'm just inventing this for you, okay? So we can spend some time putting positive numbers with normalization. And now let's assume that when they both measure 1 and 1, it's the opposite, okay? So they either get plus minus or minus plus. Okay? I'm inventing this for you. Do you see anything wrong with this table? No. Okay. Good. Now, this so far, in what I was telling you why we care about this. We care from a practical motivation, but as I was telling you, then we also care about foundations. And we need to introduce these statistics between devices. This is mathematics, and this is what I've been doing so far. But I believe many of us are physicists. So now let's do some physics with these devices. Or let's think in a physical way about these devices. Okay. In all what I'm going to do, I'm going to assume that the devices in this input-output process, they don't communicate. Okay, I can enforce this by making this input-output process defining space-like separated events and invoking Einstein causality. Okay, so I can say the process's input-output is so fast there is no time for light to go from one place to another, so I'm sure that they don't communicate. Or I can use some other ways of enforcing that they don't communicate. Maybe because I'm in Barcelona, he's in Bilbao, and I'm pretty sure that what I do here is not influenced by what Enrique does. But okay, you are super paranoid, you will use Einstein relativity to enforce this. So what does it mean, okay? So first, I'm going to use this physical principle. What does the principle, it is called no signaling, okay? There is no possibility that we signal to each other. I'm assuming this, say, based on relativity. Okay, this is saying that what Enrique sees in his location cannot depend on what I do in my place, okay? Because if it was the case, by doing different actions here, I could change what he sees, I could communicate faster than light, Okay, so what he sees cannot depend on what I do, because there is no time for light to go from one place to another. Well, this is very simple. This is just saying that the marginal probability distribution of one device does not depend on the action on the other device. Again, because if it was the case, this device could communicate by changing the statistics that is seen here. Well, this is simply saying that if you sum over these results, what this party sees, you see, does not depend on y. Because if it was dependent on y, by changing y here, I would change the statistics here. Okay, this is the no signaling principle, and defines no signaling correlations are those that satisfy these constraints. This may sound a bit, maybe it's the first time you see this concept. Let's check whether the previous numbers I invented before randomly satisfy this principle, okay? Well, of course they do, okay? Because I didn't invent them randomly, okay? So what I'm demanding is that what Alice sees does not depend on what Bob does, okay? So let's make a computation, okay? Let's see what's the probability that Alice gets +1 when she measures 0. Okay, so this is a situation in which Alice measures 0 and Bob measures 0, and the probability that Alice gets plus is the sum of these two, because I sum over Bob's result, okay? I'm just computing marginal probability distribution. This number is equal to half. But this number should be the same when Bob measures 1, okay? Because it cannot depend on what Bob measures. This is this number. And, wow, it's the same, okay? Well, I did it on purpose, okay? But what I'm saying is that this is an example of no signaling probability distribution, okay? Because all these sums happen to be equal, okay? So if you sum now over Bob, you will see that you have to take this sum plus this sum is equal to this sum plus this sum. Okay, you spend some time doing this very trivial mathematics, you will see that all these constraints are satisfied. So this is an example of a no signaling correlation. Okay, so it's fine, okay? It's a valid distribution. It can be a valid correlation for this scenario where there is no communication between the devices. Okay, first you understand that if you had chosen these numbers randomly, positive and normalized, but randomly, these conditions are not satisfied. Random numbers don't satisfy equalities. Okay, so you have to engineer a bit the choice of these numbers so that they satisfy this. So this is telling you that the set of no signaling correlations is a very specific subset of all the possible correlations, coming from a physical consideration. Okay, so what was the way people thought about how devices can be correlated before the advent of quantum physics? So what we thought is that, well, the devices have been prepared by a source or by the provider, and the provider has written a program on the devices about how to behave, okay? Or there is you can think that in the device, there is a very small daemon sitting on a chair with a program seeing how to behave, okay? And now the daemon sees the input and gives the output. So it has a piece of instructions, okay? And the instructions say, if input is equal to 3, output has to be 2. If input is equal to 4, output has to be 1, okay? So the daemon is there with the, like waiting for the input and producing the output. Okay, this is the way, I mean, I'm saying daemon, but it can be a particle, it can be whatever, okay? So this is the way we thought about correlations in the past, okay? So the way we write this is like, lambda is the instructions that are in the two devices because they were prepared by the source, they are shared, and they produce the output given the input and what is written in a deterministic way. Again, I'm assuming that there is a daemon in one box, or a program in one box, another program in the other box, and of course the output is produced given the input, but not the input of the other party, because they don't communicate. Okay, you see here there is no y, and here there is no x. Okay, I don't know if you have seen this object before. This is something called local hidden variable models, or EPR models. Okay, if you know about the EPR program and Einstein discussion about quantum physics, this is the way, this is what you have. Okay, you have a deterministic assignment of the outputs depending on the inputs and a program that potentially may vary stochastically. Okay, but this is not so critical. So this is what I'm going to call classical correlations. So this, for instance, is, in my opinion, common sense applied to correlations. Okay, you say, okay, the output depends on the input deterministically, and maybe something that is inside the devices, which is this lambda. We are quantum physicists, so you open a textbook. You don't need to read many pages. First postulates. It tells you that probabilities in quantum physics are given by a state. If you think that you have a device here and another device here, You put the measurements with a tensor product because you are assuming that they are separated, okay? So I'm assuming you all know this language here, okay? So you have measurement in the first device, measurement in the second device with a tensor product acting on the state that was coming from the provider source. So I would say that some correlations are quantum whenever they can be written in this form, as textbook in quantum physics tells me. I'm not demanding that this has to live in a given Hilbert space. So some correlations are quantum whenever there exists Hilbert spaces, states, and measurements in these Hilbert spaces that I combine with the Born rule, and I get these probabilities. Okay, so this means that within quantum physics, I can find an explanation for these numbers because I can define a state and measurements in a Hilbert space that give me these numbers. Okay, so this defines a set of quantum correlations. I hope this is clear because this has to be clear. So what do we know about these sets? Okay, what we know is that the set of classical correlations, of course, is included in the set of quantum correlation, but is strictly smaller, and the set of quantum correlations is contained in the set of non-signaling correlation, but is strictly smaller. So these sets are convex. So what I'm trying to represent here, I'm trying to represent these tables of numbers. Okay, this is in this case, these are 16 numbers, and I'm representing a vector of 16 numbers in a two-dimensional screen, okay? So you have to think that you have to play a bit with your imagination, not so much. I think it's more or less easy to understand, okay? So all the points here are these correlations that have a classical description. These points red are the points, those that have a quantum description, so I can find states and measurements in a Hilbert space that give me these numbers. And these are the ones that satisfy these no signaling constraints. You see, they are strictly excluded. They are convex, okay? I hope you know what a convex set is. They are convex. Now I can zoom in here. I'm zooming in. So this is the classical, this is the quantum, and this is no signaling. Okay, so classical is included in, of course, quantum is all this, okay? And no signaling is all this. Okay, but here is the, say, no signaling part that is not quantum, and this is the quantum part that is not classical. How do we know this? The fact that we have some quantum correlations that do not have a classical explanation, this is Bell's theorem that I'm going to tell you about. And perhaps this is less known, but I also will tell you about. So I can think of statistics between devices that go beyond quantum physics, but are compatible with Einstein causality. I can think of this. I can write these numbers. I don't know which theory is behind these numbers, but I can think of these numbers. Okay, you see, in these correlations, I can associate numbers without thinking of any theory. Okay, then I can check whether these numbers are compatible with a given theory, but I can invent them. Okay, so it seems that we need to understand a bit this gap, okay? So I'm going to tell you about Bell inequality. So why do I have to understand this? Because remember, one of my motivations is to do quantum information theory for black boxes. So if I want to do quantum information theory with black boxes, I have to understand how quantum black boxes can be correlated. So I have to understand this region here. I have to understand this boundary because this boundary tells me how quantum devices can be correlated. So I have to understand this. So let's understand this. Let's try to see these sets, okay? And for that, I will do a course on Bell inequalities. So what is a Bell inequality? Again, this is the source, the provider prepares two systems. Now, I hope you will follow me. I'm going to change again the notation. Now the measurement, I'm going to call it 1 and 2, and the output I still keep plus and 1. Doesn't mean anything, okay? It's just convention. But this convention is useful for what I'm going to say. So I'm going to explain the Bell inequality with the most famous inequality that is Clauser-Horn-Shimony-Hall. Clauser got the Nobel Prize in 2022, together with Alana Spee and Anton Zeilinger for experimental Bell demonstrations. Okay, but now I'm going to just tell you, who knows about CHSH Bell inequality? Don't be shy. Who knows? I mean, you can say, you know, guess, but not so many people. So then I will explain it, okay? Sorry for those who know. So what is a Bell test? Again, there is a source that prepares a system. This goes to Alice. Alice makes two measurements and gets two outputs, plus and minus, and the same plus, okay, for Bob, okay? Now I'm going to take this combination of the statistics I see. A1 is the output of the first device when the first input is used. And B1 is the output when the first input is used. A2 is the output of this device when the input 2 is used, okay? And all those is the product, these are the product of the two outputs. So this product can be plus or minus 1, okay? So I'm taking the sums of these signs, let's say. Okay, so in classical physics, we know that these values may vary with time, but they are plus or minus 1, okay? So they have values plus and minus 1. So it's very easy to see that if you take values plus and minus 1, this quantity is bounded by 2, okay? So this is very easy. So you can you only have to assign plus and minus to A1, B1, A2, B2, okay? So you have 16 possibilities, 2 to the 4. You can list the 16, and you will get easily convinced that this can never be larger than 2. In fact, it's only 2 or minus 2, because since there is this sign, there is always a cancellation. So it's 2 or minus 2. I mean, do it, okay? But this is your exercise. I mean, if you want to have an example, let's imagine that you say, the daemon or the program says, no matter what the input says, you always say it's plus 1 as an output. Okay, so you know that A1, A2, B1, and B2 is equal to plus 1. Let's compute together CHSH in this case. This is plus 1 times plus 1 is plus 1. Plus 1 times plus 1 is plus 1, 2. Plus 1 times plus 1, 3. Minus plus 1 times plus 1, 3 minus 1, 2. Okay, this is a Bell inequality, you see? I mean, super deep mathematics. This is a Bell inequality, okay? So this quantity is bounded by 2. Okay. So this is so simple that sometimes when I give talks, I didn't do it, I play a Bell test with people in the audience, okay? So I give to people a list of questions, 1 and 2, and I give them some, they have to give an answer. The answer is in the form of some shapes, and I compare the results, okay? I can do this physically. We can do this, okay, here, and you will see that you will never have a value larger than 2. I think you can also give to, I don't know if you have been in Barcelona, we have this street, La Ramblas, okay? Sometimes in La Ramblas there are these people who fool tourists with some games, and people bet money, and they get all the money. I'm sure you can go to the Ramblas and find people with some education, and there will be people willing to bet money that this quantity can never be larger than 2, because they can compute 1 plus 1 plus 1 minus 1, 2. Okay? So this is clear. Well, the surprising thing is that if the source prepares this entangled state and you make these measurements, then this quantity is larger than 2, it's 2 squared root of 2. Okay, so this is the violation of a Bell inequality. This is the first time that you see quantum physics in my explanation. So this is telling you we cannot do this. This would be a nice application of quantum physics, that we cannot do it in our scale. This is done in the labs, okay? But if we could, Enrique and I could prepare this state, okay? Put of 2 particles, 2 qubits. I put this particle in my pocket. We cannot do it, unfortunately. He puts this particle into the pocket. We go to the Ramblas. We get an input. Depending on the input, we take the particle out of the pocket. We make a measurement, and we give the output depending on the measurement result. We would be having CHSH larger than 2 and gaining a lot of money. Okay? Because I'm sure people are willing to bet that this quantity cannot be larger than 2, but this is in classical physics. Okay? So if you are not surprised by how come quantum physics can get something larger than 2, my talk is a failure, because you have to be surprised. Because I was simply summing 1 plus 1 plus 1 minus 1, and I'm violating this. Okay, so I will come back to this. So how come I can violate this, okay? Because I'm summing ones and minus 1. This is bounded by 2, okay? This is mathematics, and this is correct. So what was wrong was my initial assumption, which is not true in physics. Observables have not well-defined values before you make the experiment. Okay, so the spin of a particle is determined by the experiment. It doesn't exist before making the experiment. And since this is not true, then all what follows is not true. Well, it follows, okay? If you violate this, it cannot be that 3 pluses and minus a plus a minus, it gives something larger than 2, okay? So it simply means that this was wrong. And you see with this, I'm using all what I reason always with this CHSH parameter, okay? So I'm invoking all with the statistics, all the experiment. Now, what is a Bell inequality? A Bell inequality is precisely the frontier you have here between classical and quantum world. Okay, it's a boundary satisfied by the classical world. So this CHSH in this representation is like a hyperplane. And saying that something is smaller than 2, it's telling that the classical world is all down there in this direction. And these are the points that violate CHSH. And this is why I know that in quantum physics there are quantum correlations that do not have a classical explanation. I don't know if I was told some years ago that Bell inequalities can be found in papers by Boole, the inventor of Boole's algebra, before quantum physics. Why? Because there is nothing quantum in a Bell inequality. It's just boundaries of the classical world. You don't need quantum physics to find a Bell inequality. You need quantum physics to violate it, but not to find it. Okay, so this is the quantum world. So how do I know that there is something beyond quantum physics without violating the non-signaling principle? Remember this innocent point that I invented for you, okay, randomly? Let's compute the value of CHSH for this. A1, B1 is either plus, plus, or minus, minus, so the product is plus. This is plus. This is plus. But for the last one, the product is minus, plus, or plus, minus. It's minus. With a minus here, it gives 4. So this point, innocent point, gives CHSH 4, which is not possible with quantum physics. I didn't prove it to you, but you can prove that in quantum physics this is bounded by 2 square root of 2. So this means that if by chance you make an experiment where you make 2 measurements of 2 outputs and you see these statistics, you are falsifying quantum physics in the same way as Bell, in a violation, falsified classical physics. Where to find these points? I don't know. I don't have any theory beyond quantum physics, okay? But one day, maybe, you will make an experiment, you will detect these points here, and you will be falsifying quantum physics. Okay, so, I'm talking a lot. So, I started with motivations about devices, and now I'm changing to this correlation. I'm telling you about theories beyond quantum physics, the quantum boundary, and more fundamental aspects, okay? But here, remember, it's because so far I'm interested in understanding what I can do with quantum physics, so I'm interested in this region. So I don't have time to tell you this, but we have tools to characterize this region, okay? We can use them. So now so I started with information devices. I now jump into this language of correlations, Bell theorem, and now I go back to information devices, okay? And now let me present you the first protocol for device-dependent randomness generation. Remember the joke where you want to buy a device and you want to be sure about randomness. Okay, so what you have to do if you want to have proper random number generator, you have to go to the provider and ask for a Bell test. So you as a user go and you ask 2 devices and you spend some time and you see if these devices violate a Bell inequality. Okay, so what you have to do Bell certified, this is Bell certified quantum randomness, okay? The randomness is certified by the Bell violation. Why is it certified? These outputs produced by the device have to be random if they violate a Bell inequality. If they were not random, it means that someone could predict them. Okay? This is the definition. If something is not random, it means that someone can predict. If someone can predict these numbers, this person can write what these numbers are. Okay, it can say, I can predict that output when you make the first measurement will be +1, and the output when you make the second measurement will be -1. This is predicting. But if you predict the numbers, you can write them, you cannot violate the Bell inequality. Okay? So the output of a Bell experiment must be random. And then you can be sure about randomness, and this guarantee of randomness comes from the Bell inequality violation. And you can mathematically quantify the amount of randomness, so this is something that we got in this paper. So from the Bell violation, you can bound what is the predictability by anyone, okay? So at the point of no violation, remember the classical boundary was 2, you have full predictability, but as soon as you have a violation, then you have some lack of predictability, hence randomness. So this is a way that you can be certain about randomness in a quantum experiment. And this is why you can buy a device-independent Bell-certified quantum randomness generator. So the provider will tell you, this is quantum randomness. Okay, I will check myself. And then you make the Bell test, and you know that the outputs have to be random. And the same idea can be used for cryptography. I don't have time. I mean, you can use the same idea for cryptography, okay? You have to do, Alice and Bob, or Enrique and I, we have to buy these devices. We have to see a Bell violation. If we see a Bell violation, we know that this is random. He knows that this is random, okay? So we have something that no one knows. It's only on our hands. But a Bell violation is obtained by measuring an entangled state. So these random outputs are correlated. And correlated randomness is a secret key. Okay, now I'm jumping a bit, okay, but you have to understand that the same idea can be used to make secrets at distance. Okay, so more in general, this is what in my group, one of the main themes in my group. So we work a lot on this quantum information theory with black boxes, and I want to finish. I don't know how much time I have, not much, maybe. Okay, well, I will go fast. So I was focusing a lot on quantum information theory. Now I will go with the final result on quantum foundations. Okay? So I was mostly using Bell theorem and correlations to design protocols for randomness and cryptography. Now I'm going to use what I learned here to say something about quantum foundations. Okay, and this is something that we published a bit more than 2 years ago. So what is the question we want to address here? Again, if you open the textbook in quantum physics, you look at the postulates. Okay, you find the first postulate in the Hilbert space formulation. Okay, it tells you that to any physical system you associate a complex Hilbert space of a given dimension. This is the first postulate of the theory. And then it tells you that the state is a vector, that the measurements are given by a basis, the probabilities are computing with a Born rule, and that you join systems, you put a tensor product of the Hilbert spaces. These are the postulates. You don't discuss them. You accept them in the Hilbert space formulation. I mean, if you think historically, quantum physics was the first theory whose postulates deal with complex numbers. I mean, if you think about Newtonian physics, the objects you deal with in the theory are forces, acceleration, masses, all real numbers. Okay? If you think about electromagnetism, fields are real. We sometimes use complex numbers to simplify calculations, but the objects are real. In quantum physics, I mean, from the very beginning, your objects in the theory are complex. I don't know if this worried you, but you may think that it's weird, no? Well, quantum physics is weird in a way, but okay, this is weird. And it's not only, I mean, maybe even the founders of the theory, okay, so they even express that, okay? There is this quote in a letter from Schrödinger to Lorentz where probably psi is a real function. So the question is, what happens if now I replace complex number by real numbers in Hilbert space quantum theory? So what I'm going to do is I'm going to take the postulates and I'm going to say what happens if I use real Hilbert spaces, okay? Well, of course, we know that to describe a complex space, I need complex number, I need two real numbers, so probably the dimension will have to grow because I need to accommodate more numbers. But maybe the only reason why we use complex number is a matter of economy. With the same dimension, I can put more numbers, but still there is no fundamental reason to choose between complex and real Hilbert spaces. So this is a question that has been considered in foundations. So people wanted to understand if we really need complex numbers in quantum theory, or you can do the same with real numbers and keeping the same theory. So are two different theories, or they lead to the same predictions? Because if they don't lead to the same predictions, I can make an experiment and falsify real quantum theory. If they lead to the same predictions, no way I can falsify real quantum theory. It's just a matter of convenience. Just to illustrate my point, I will show you that you can, any experiment of this form in complex quantum theory, you can express in real quantum theory. Okay? So just for you to understand, what I'm going to do is some sort of Bell theorem for real quantum theory. Okay, so in Bell theorem, you can understand as a game. There is someone who believes in local hidden variable models, classical correlations, and there is another one who believes in quantum correlations, and this quantum physicist designs the CHSH test, makes the CHSH test, he sees a value larger than 2, and challenges the local hidden variable guy to predict this. And of course, he won't be able to do it because I proved to you. So now there is something similar here, okay? So there is Enrique, who is a complex physicist, but in the sense that he believes in complex quantum physics, okay? He wants, but I don't believe in complex quantum physics, I believe in real quantum physics. He has to design an experiment that I cannot explain with my theory. If he does it, he wins. If not, I win. So Enrique is a good physicist, so he starts by the simplest he can think of. So you have a state and you make some measurements, and he does it with complex matrices, no? Complex Hilbert spaces. So what it means, the experiment is described by the statistics, okay? So he has a complex state and a complex measurement and describes probabilities according to the quantum rules. Everything is complex. He comes to me and says, show me how to get these numbers in your theory. Well, easy, okay? So what I do, I take the matrix that he was using, okay? And I double the dimension. Of course, I know that he's using a given dimension for complex numbers. I will have at least to double the dimension, okay, to accommodate this number of parameters. I don't have time to tell you, but I can reproduce the same statistics with real operators. Okay, so all what you see in experiments is statistics, okay? So he has to produce some statistics with his theory that I cannot reproduce with my theory, and then he proves me wrong. You can do it, okay? This is not, this is easy. This was known. Then he may say, oh, maybe what I have to do is something similar to Bell. I have to prepare a state of many particles, send them to different locations, and then he designs a Bell test, a sort of Bell test, okay, with particles going to directions. He computes these correlations that I was telling you before, and he comes to me and says, Tony, derive these correlations with your theory. I don't have time, but I can do it. Okay, I didn't prove it. So this was proven in this paper, for instance. Okay, so for a long time, it was believed that there is no way you can falsify real quantum theory. So at the very end, it might simply mean that the need of complex number, there is no need for complex number. It's just a matter of convenience. Well, what we proved in this paper is that if you have a more complicated setup in which you have 2 states and 3 measurements, okay, so you see, then Enrique can design a complex quantum experiment that I cannot reproduce with my real quantum theory. So he can design an experiment in which this source prepares a maximal entangled state of 2 qubits, this source prepares another maximal entangled state of 2 qubits, you make measurements here and here and here. So according to quantum theory, this has to be the trace of the state here, tensor product, the state here, measurement here, tensor product, measurement here, tensor product, measurement here, everything combined with a trace, as the postulates tell you. And now he comes to me, and I have to do the same, but instead of using his complex matrices, I have to use any real matrix that I want, as large as I want, okay? So what we prove is that you can never achieve that. Okay, so here he has a quantum experiment that I cannot explain with real quantum theory. If you make the experiment, you falsify real quantum theory in the same way as Bell inequality evaluation falsify classical physics. In fact, I mean, we published this paper, and immediately some experiments came, and it was falsified. Okay, I don't have time to do this. I'm always ambitious with my talks, okay? There is more, eh? So, yeah, just in case, I mean, but yes, so it's time to finish, okay? So the purpose of my talk was telling you about this way of reasoning about devices as black boxes producing statistics, okay? Of course, physics is in the working of the devices, but I only assume the theory governing these devices, but not all the physical details, all the physical modeling, okay? And I'm dealing with this because it gives protocols with self-certified performance. I can be sure about quantum randomness because the statistics produced by the devices that violate a Bell inequality guarantee that the outputs are random. And it's also nice from me, I always liked Bell theorem because it's a theory in which the resource, what you use, is the violation of Bell inequalities. Because you want to achieve things that are not possible in classical information theory. The only way you can certify that you are seeing some statistics that is not compatible with classical theory is if you violate a Bell inequality. So it's necessary to see a Bell inequality violation, sometimes not sufficient, but it's necessary to see a Bell inequality violation to conclude that you are doing something beyond classical theory. So I rather quickly told you about protocols for Q distribution and randomness. I didn't tell you about self-testing. So one of the main themes for those people who care about this question is about the limitations and possibilities of this scenario. Okay, at least I didn't have time to tell you. And also, I just told you how using the same language of correlations produced by boxes, we can shed light on quantum foundations. For instance, we had the tools to falsify real quantum theory, okay, something that was believed not to be possible in the past. And more in general, this is also another topic of interest, like we are interested about certification, okay? This is something very transversal to the field, so you want to understand how devices or very complex systems that are prepared in labs can be certified, and you can conclude that something is quantum random, quantum secret, is a quantum computer, is entangled, so this is in general, we want to understand what you can say about these complex quantum systems with our limited interaction with the devices and with the statistics that the devices produce. Okay, this is well all. Thank you very much for your attention.
Questions or comments?
Hello, thank you for the talk. Why are the tests a test for the device, for the devices, and not for the source of entanglement?
Yeah, well, I mean, well, there are two things. First, in my narrative again, I care about the users, not about the provider. So the users go to the provider, which is the source, and the provider gives the devices to the users, and the users go back to their locations, and they want to test the devices they got from the provider. Okay? But of course, the information they get with this also tells things about what the provider did. For instance, we know that the only way you can violate a Bell inequality is if the provider prepared an entangled state. So by making a Bell test, I also know that the state the provider prepared is entangled. Okay, so we also get information about the devices and somehow about the provider, okay? But in this is something I forgot to mention in my talk. All this device-independent language always cares about the poor, ignorant user who doesn't know quantum physics, I mean, who knows little of quantum physics, and who is never going to open the device. And even if he opens the device, he doesn't understand the physics in the device, okay? So I want things to be device-independent for the users. The provider should better know quantum physics, okay, because he has to make the device, okay? So things are never device independent from the provider point of view. He cares a lot about the physics. So for instance, if we want to make cryptography in a device independent way, we go to the provider and we ask that he gives us devices to violate a Bell inequality. So the provider will think about the physical details of the implementation given a Bell inequality violation. So he will prepare the right state and the right measurements for us to observe the Bell inequality violation. Because if he doesn't do it, we don't buy the devices. Okay, so I think what you do, usually this device independent certification, it cares about the users. And the provider, usually we leave it out of this picture, okay, because he's supposed to have good understanding of what's going on.
Okay, thank you.
Comments, questions?
So classical physics or local realistic theories have been, well, falsified by Bell's theorem, and you have shown that real quantum mechanics was falsified in this, well, more complex network. Can you think of any other theories that you could falsify in such a device-independent way, or do you think this is it? This is all you can do?
I think, so this scenario, I think it's nice because it allows you to think about, so for instance, if I go to the picture with all the correlations. Yes, okay, let me just put it here. Yes. So this language is nice because it allows you to think about points that are not even possible with quantum theory. You can in principle write them, okay? But of course it has limitations because this scenario, it only cares about statistics. There is no dynamics, okay? So I don't have any unitary or Hamiltonian or anything like this, okay? So it has limitations. So in particular, we don't have so many theories to falsify, let's say, okay? So you can invent them. Real quantum theory was a natural candidate that people thought that it was unfalsifiable. Now, okay, if you tell me the theory, I can try to understand the structure that is within the theory and find limits on the correlations. But usually, I don't know, if you have any candidate, I'm happy to know, okay?
I wanted to say, of course, you could falsify quantum theory in the same way.
Yes.
But what I meant is, at least you could think of an experimental setup to actually do this and not just in principle.
Yeah, but the problem is, like, for instance, okay, in the field, there was a time where people were trying to understand, okay, why this region, we don't see this region in physics. In principle, why we don't see this half, 0, 0, half, 1? It looks super innocent, okay? So why I don't see this table of probabilities? And then the answer that people were telling you is like, because I cannot find Hilbert spaces, define a vector in the Hilbert space, measurements for the Hilbert spaces, combined with the tensor product, compute the trace, giving me these numbers. Well, it's not very satisfactory from this point of view, okay? Okay, you may say, because I would be falsifying quantum theory. Okay, then we talk, okay? But let's say, also you can say that the answer why these points here are not possible is because I cannot express them with Hilbert spaces, okay? So people try to think about ways of discarding these points based on operational considerations. So for instance, we know that this half, 0, 0, half point would render something that is called communication complexity trivial. I don't have time to tell you, but would render something that is supposed to be complex trivial. We believe that this cannot be the case. This gives us a reason, not based on Hilbert spaces, to eliminate this point. So there are some efforts in which people try to understand what would be the consequences of these points here and try to remove them based on operational considerations, not based on Hilbert spaces. I'm not answering your question, but I think this is something that you can try to do.
Okay, thanks for the answer and for the talk.
What was the final takeaway on the inequality you made for real quantum physics versus complex quantum physics? Was it disproved? Did I hear you properly, or what happened in the end?
The logic is the same as Bell inequality, okay? So you have an expression that you can compute in the experiment, and you know that for Bell inequality, for classical physics, this expression can be at most 2. Then you make the experiment. Well, first you can see with your calculations that quantum physics gives something larger, and then you make an experiment and you get this larger value, and you falsify classical physics. This was Bell theorem. So we did something similar, okay? We had an expression that you can compute too many slides. We had an expression that you can compute in this experiment, okay? And we got a bound for this expression for real quantum theory. That is, when probabilities are this form with real operators of arbitrary size, okay? This is why the problem is not easy, because you have to find put in any size, any matrices of any size here, okay? And we give an expression, an inequality based on these numbers for real matrices, and we proved that there was a bound, mathematical bound. And then we proved that this bound was violated when these matrices were complex. And then people made the experiment, and they got this value larger than the bound. Then we were falsifying real quantum theory in the same way as Bell inequality violation falsified classical theory. I mean, I think this is the nice thing about this language is like, so imagine you make an experiment, and so there is an experimentalist and a theorist, and the experimentalist, they make an experiment, and then where you have, I don't know, you believe that you're measuring polarization and of some particles, and you generate some statistics. Now the theorist tries to reproduce these statistics with quantum physics. So the theorist said, okay, you were measuring polarization, so I have to use matrices of size 2 times 2, okay, because polarization or spin 1/2 particle. He tries to reproduce everything, the theorist fails. Okay, does it mean that the theory is wrong? No. It means that the theorist is proposing, the model the theorist is proposing in quantum theory based on matrices of size 2 times 2 is not able to do that. So to prove that the theory is wrong, you have to exclude any possible explanation in the theory. So you may say, you thought that the dimension of your particles was 2, but actually it's 3. And then you have to try with the systems of dimension 3. If you fail, it doesn't mean that the theory is wrong. It means that the models you have been trying for your theory are wrong. Then you have to try matrices of size 4. Okay, so quantum theory are all possible Hilbert spaces. Okay? So this is why here you have to, real quantum theory, you have to falsify all possible real matrices of any size.
Thanks a lot for your talk. Maybe from a more technological point of view, so let's say the status of quantum computing is more or less, we all know, is not very good for the moment, right? But what about the status of the quantum communication or cryptography? So the companies are already selling devices that you can consider totally secure, or I mean, or they are secure because the hacking is so hard that, I mean, only people with a very, I mean, extended knowledge know. So
Yes.
more or less, which is the status? So.
Okay, so well, first of all, there are companies. I would say not many. Okay, I would say that well, first there are not many. Second, usually. So I have a very good friend who is the owner of one of the companies selling cryptography. He doesn't tell me who are the customers or whether he sells, okay? Because if you buy cryptography, you never explain which cryptography you use because this gives you a weakness. So I don't ask him. I know he cannot tell me, okay? Maybe sometimes we go out and I can try, but I never try, okay? He's my friend. So people don't tell you, don't give you this information, okay? So I don't know. What is clear is that cryptography is quite conservative. It has to be, in a way. So not so many people are adopting quantum key distribution. They remain with the previous methods. Okay, there is a market, small. My hope is that, but we shall see, is that people will understand that here you only gain, okay? Because before you were encrypting messages based on complexity of some problems, and now you have a new tool, which is quantum physics. So you have complexity of problems and quantum physics. You try to combine the two, okay? You will only make more robust protocols. So this is what the field, at least in the quantum part, tries to do, okay? They try to see how quantum physics can be combined with computational security, like standard protocols we use today, and combine them and make stronger protocols. Okay, this is first answer, but still the market is not super large, okay? Second thing, I mean, the market will become large if there are many successful hacking attacks on the existing protocol, okay? Then people will adopt the new solution. So the second thing is that there is something you said in your question that I try to avoid, okay? This I was writing in my papers when I was young and naive, which is unbreakable security, okay? We should never say that, and this was understood, okay? So I was writing unbreakable security for some protocols that were hacked. So what we have to understand, and this has to be clear, is that cryptography is a very complicated issue, okay? So there is a parameter that is also relevant, which is the salary you pay to the guys running cryptography, okay? If it's not large, then this is a weakness, okay? So in the Universitat Autónoma, there was a place where they had a pad with a keyboard to enter, okay? That was secure, and 4 numbers were more erased than the others, okay? Well, so there is nothing unbreakable. Okay, so this is a component that allows you to generate a secret key, and the hacker has to understand quantum physics to try to find vulnerabilities.
Thanks.
So thank you very much for the talk. So there is, I don't know if I can formulate the question correctly, but there is a way to do like faster than light communication if you are able to clone quantum states once you have an entangled state and so on. But there is this no cloning theorem that prevents you from doing this. Is there something similar? So does a non-signaling theory somehow impose a known cloning equivalent in the box, or?
Yes. So we have a paper with our colleague Luis Massanes in which we studied. So there are some properties of quantum physics, like no cloning, okay? And what we try to understand is which properties you could extend yes, to this part, okay? And no cloning is one of them. So you can, for black boxes, you can have an analogous of no cloning, and it follows from no signaling. If you add cloning, okay, then you could also violate no signaling. Yes. So I can send you the reference if you are interested. Yes. So you write me and I will send it to you.
More questions, comments? So if not, we think again, Tony.